All right, I've got a setup here, or I've got a horizontal beam. It's got a load Q kind of in the middle there. And basically I've got two columns. One's pinned, that CE is pinned, DB is fixed pinned. And I want to make sure that neither one of them buckle. Now, I believe they're both square cross sections. Okay, 0.625 inches, so 5/8 of an inch. Okay, I know A is acting 12 inches from B, and basically I want to find out what Q will be so neither one of these will buckle. So the first thing I'm going to do is I'm going to basically figure out the force through each one of these columns. Then once I have that force, I'll figure out the critical load through each column, and then whichever Q is the smallest is the one that I can't exceed, right? So I've got B here, and I've got C here. Okay, so if I sum my forces in the y direction, I have B plus C equals Q. Okay, then if I sum my moments, I'll do it about point B. Okay, I've got negative 12Q, right, because that A is 12 inches. So negative 12Q, and then plus 40C equals 0. Again, that's the moment about point B. From that, I learned that C equals 0.3 Q, which means B is 0.7 Q. Okay, so now I have B and C relative to Q. So I know, how much of Q is going through B, how much of Q is going through C, essentially. And it makes sense that B is seeing more of the load because Q is closer to B. Okay, we just use statics to figure that out. Now I'm going to use my critical load equation. Okay, which, if you've forgotten, is pi squared EI over KL squared. Okay, and I'm going to do that for both B as well as C. So we'll start with B. Okay, so the force through B is 0.7 Q equals pi squared. These are all steel, I'm assuming. Oh, yep, it gives me E is 30 times 10 to the 6, gives me that in the problem statement. I is, for a square cross section, it's 1/12 BH cubed, which B and H are the same here, so it's going to be 1/12.625 to the 4th for a square cross section. Okay, and then that's going to be divided by K. Now, this is where we have to look at. I've got a fixed pinned. I go to my chart in the book to figure out what my effective length is for a fixed pin, and I find out that it's 0.7. So this will be 0.7 times the 35 inches, all of that squared. Okay, so again, I found out what my load is relative to Q. Okay, and I set that equal to the critical load, which again, I have that whole equation there, using the effective length for a fixed pinned, which is 0.7. From that, I learned that the Q, Q critical, so to speak, is going to be 8960. So if Q is 8900, then that column will buckle. Now I'm going to do the same thing with column C. Whichever one's smaller is the one that I cannot exceed. So I get 0.3 Q equals pi squared 30 times 10 to the 6. I is the same as it was. It's the same cross section, so 1/12, 0.625 to the 4th divided by, and really the only difference here is this denominator, okay, and the load acting through it, the 0.3 Q. Okay, this one's pinned, so this one has a K value of 1, right? That's kind of the default, is the pinned, times 45, all of that squared. From that, I find that Q would have to be 6197. Okay, so this is the smaller one, so this is the one I can't go beyond, because at 6,200, column C is going to buckle, okay? It's not till about 9,000 where column B is going to buckle. So if I'm up at 9,000, yeah, B will be okay, but C will have long since buckled. So my critical load, my absolute maximum I can do is 6197 on this sort of a situation.